You take your headphones off. Take your headphones off. All right, so we're going to start by talking about scientific notation. This is on your Intro 4 worksheet. It's right along with the significant figure, so we're going to use this as kind of a little review for Sig Figs and an intro to scientific notation. Yes, Ken? Okay, awesome. So, scientific notation. Got to talk about when to use this first. It's used to express either a large number or a small number as a decimal between 1 and 10, and then it's multiplied by a power of 10. Okay, so I'll kind of show you how that works. Okay, so we're going to start with just an example. Now, these three right here, those are on your worksheet. So this is M, O, and J, I believe. I think. I don't know. Yeah, it is. Okay, so the first step when we're doing scientific notation, we got to figure out how many significant figures our number has. So we are trying to write this 100 grams in scientific notation. So we got to use our absent Atlantic and present Pacific method. So we're going to look, there's no decimal point, so we're going to start on the right side of the number. We count at the first non-zero, so these two don't count. That one counts, so there's one significant figure here. Okay, so that means that when we write scientific notation, our scientific notation also has to have just one significant figure. No more, no less. Okay, so now when we write this in scientific notation, remember we're going to write this as a number between 1 and 10. So where we need to put the decimal point is obviously between this 1 and the 0 here, so we're just going to write 1. And then it's times 10 to a power. The power is going to depend on how many places I moved the decimal. Okay, so right here, I know obviously we said the decimal is absent. That's just, it's still there though, right? It's absent as far as what we're looking at here. Okay, so we would count 1, 2. We moved it 2 places, so the exponent is 10 to the second. If we move our decimal left, the exponent is going to be positive. If we move our decimal to the right, which we'll do down here, our exponent is going to be negative. So that would mean that it's a number that's smaller than 1. Bigger than 1, numbers bigger than 1 are going to have positive exponents. Numbers less than 1 are going to have negative exponents. Okay, so let's move on to the second one. I picked these two on purpose, right? They're both 100. One of them has a decimal point, one of them does not. Okay, so if we look at this one, now it's present. We start on the Pacific side. We count 1, 2, 3. So we have 3 significant figures. The difference between these two numbers is that we know for certain when this decimal point is here that somebody would have measured and estimated to this ones place. Okay? The difference up here is that we have no idea what these values are. Like this 0, it could be a 1. It could be a 114. That could be accurately measured. But the thing that we measured with was only calibrated out to this hundreds place. Okay, so we can't just assume what these other values are. Okay, that's the difference between these two numbers here. In this case, we know exactly that this is 100% for sure 100. This one we do not. Okay, that's the difference. So now, same thing, we move the decimal place twice. We need to write 1.00 times 10 to the second. Okay, it's 1.00 because we need 3 sig figs in our scientific notation. Okay, moving on to J. J, once again, we have a decimal point that's present. Okay, so we're going to start on the Pacific side. We start counting at our first non-zero. So that'd be the 3 here. And we count 1, 2, 3. So we have 3 sig figs. Okay, to make this number something between 1 and 10, we're going to have to put the decimal between our 3 and our 4 here, right? So we would call this 3.40 times 10. And it's going to be obviously to a power that we still need to count here. Girls, it might honestly be helpful if you just come and either sit in the middle or something. Like you're going to constantly be laying around if you want to, since there's space. But if you don't want to, that's fine too. All right. Now, we got to count how far we moved the decimal. So we moved it 1, 2, 3, 4, 5, 6, 7, 8, 9 places. Okay, if it's right, we're reducing, our number is smaller. Okay, so that's going to be a negative exponent here because our number is less than 1. So it's going to be to the negative 9th. Okay, we're going to go through these, go in the opposite way pretty quick here. When we go from scientific notation back to our numerical value, we need to also be mindful of our significant figures. Okay, so here we have 3 significant figures, so we write 3, and sig figs are easy when we do scientific notation because however many numbers are here, they're all significant in scientific notation. Okay, now it's a negative number, that means our number must be less than 1, so we're going to have to move the decimal to the left here. So we move it 1, and then 5 more spots, so I'm going to have to add 5 zeros. So it would be 0, 0, sorry, 0.00000835. Remember how I did that? How I got all the extra zeros? I would have had to move this 6 spots. So I would have 1, 2, 3, 4, 5, 6. Each of these gets a 0 filled in here. Sorry, I need a little more space. Very last one, 1.202 times 10 to the third. First of all, it's going to have 4 sig figs, right? These are all significant. 1, 2, 3, 4. So that means my answer over here has to have 4 significant figures. Okay? It's times 10 to the third. It's not negative. It's positive value. So we know it's going to be a number greater than 1. Okay, so we're going to move the decimal 3 spaces to the right. 1, 2, 3. So our number is going to be 1,202. Questions on scientific notation? Beautiful. Let's do it. Next we got percent here. I believe this is on the back side of your sheet. Intro 4. I'm going to actually do the first one in a second here. You might want to write this equation down. Percent error is telling us how accurate a measurement that we take is, or how accurate something that we do in the lab is. Okay? So for our example here, we'll say that I was trying to find the boiling point of water. So let's say I went into the lab and I found the boiling point of water. So I went to my lab, stuck a thermometer in water, got up to boiling. When it started to boil, let's say it's at 92 degrees Celsius. That 92 degrees Celsius, that would be my experimental yield, what I found in the lab. So by experimental here, this is what you get in the lab. That goes with experimental. Okay? Now, we all know that the boiling point of water is not actually 92 degrees Celsius, right? It's 100 degrees Celsius. That 100 degrees Celsius, that's what the theoretical value is. So that's the accepted value. So the value that scientists that are smarter than us have found it to be. Okay? So that's our accepted value. So we take our experimental yield, so we take our 92 degrees Celsius, we subtract our theoretical yield, which would be 100 degrees Celsius, we know, and we divide the whole thing by the theoretical or the accepted yield. Okay? This is absolute value here because sometimes we get a negative number here and we don't want a negative percent. So we take the absolute value, we times by 100, that gives us our percentage. Okay, so we're going to do this with an actual problem. This is letter A that is on your sheet, so you can follow along, get that one done right now. Okay, it says that John uses his thermometer and finds the boiling point of ethyl alcohol to be 75.5 degrees Celsius. He looks in a reference book and discovers that the actual boiling point of ethyl alcohol is 78.3 degrees Celsius. What's the percent error? So our experimental, remember, is what John is going to find in the lab. So he finds it's 75.5 degrees Celsius. So the first thing that you're going to write is 75.5 Okay, then he looks at his reference book. He finds that what the accepted value of the experiment, or the theoretical, value actually is 78.3. So we subtract 78.3, and we divide that whole thing by 78.3, or the theoretical value. We take the absolute value, we multiply it by 100. And that's going to give us our percent. It's going to tell us basically how accurate we were, how good we did in the lab. Okay, so when we do this, we're going to get negative 0.0358. Take the absolute value of it, times it by 100, we get 3.58% error. So he was pretty accurate in the lab. Okay, anything generally speaking between 0 and 5% is a very good percent error. All right, while we are on the subject of labs, we're also going to talk about precision versus accuracy. The reason we're talking about this is when we talk about being precise versus accurate, and we know what these terms mean, it can help let us know how we are doing in labs and what's going on in a laboratory setting. Okay, so you're going to hear me say things like precise or accurate or both sometimes. Okay, so when we talk about something being precise, and now this is on the front half of that sheet. We're not going to actually go through an example, but that's where the questions are that are related to this. So when something's precise, what it means is it's basically a repeatable action. So it means you're finding repeatable results each time. Okay? So for example, if John's precise, he's going to get right around 75.5 every single time he does this experiment. So let's say he does 75.5. Usually you do things in sets of 3. So let's say he does it again, and now he gets 75.4. Time after that, he gets 75.5 again, maybe. He's very, very precise. He's getting the same thing, or close to the same thing each time. It's very repeatable. Okay? Accuracy, on the other hand, is how close we are to an accepted value. So now this would be like if John got 78.0, 78.6. He's right around the accepted value. I mean, in this case, we said that 3.58% is actually pretty good, too. So it's possible to be precise and accurate as well. Now, if John were to do his experiment and he gets 70.0, 69.8, maybe 70.1, he'd be very precise, but pretty inaccurate. Okay? And what that might tell him is that maybe there's something wrong with the equipment that he's using, because he's obviously doing the same thing every single time, but maybe his equipment's it's not working how he wants it to. Okay? Or maybe one time he gets 70.0, one time he hits it right on the head, one time he gets like 80 something. So if you're getting big differentiation in results like that, it might tell you that what you are doing is the problem. So there's some human error involved. Okay, so that's kind of how we can use that to help us out in the lab setting. Okay, next, we're going to talk about significant figures in math. So this is going to be multiplying, dividing, adding, and subtracting with significant figures. Multiplying and dividing are going to have the exact same rules. Adding and subtracting are going to have the exact same rules. For multiplying and dividing, you're going to do the multiplication and division problem. Okay, when you get done, you're going to be rounding your answers. The answers have to be rounded to as many Sig Figs as the least precise number in the problem. Okay, so that's the number with the fewest amount of significant figures. I'll show what that means through an example here. So the first thing that you got to do, and I've already done it for you because we're not really caring about how well we can punch things into a calculator. First thing that we're going to do, multiply the numbers in the problem. So we did that. We got 6.38. Okay? Next thing that we got to do, we got to figure out how many significant figures the numbers have. Okay, so we look on here, It's pretty simple. There's not even any zeros involved, so we know that each number must be significant, right? So right here we have 3 significant figures. Here we have 2 significant figures. Okay, so how many significant figures does our answer need to have? 2, exactly. It needs to have 2 significant figures. So what that means is that we need to round to those 2 numbers. Okay, we don't get to pick like this number and this number, right? It's the 2 that are next to each other. So that means that we're using our 8 to round this 3. Okay, so we take a look at the 8. Okay, is it 5 or more or less than 5? It's 5 or more, right? So we're going to round up. So our answer is just going to be 6.4. All right, the next one. Same thing, I already did the math. Okay, so now we got to determine what's the number with the least amount of significant figures here. So we look, this one has 4, this one has 2, this one has 3. So we're rounding to how many sig figs again? 2 of them. Right. Okay, but where are we rounding on here then? Like which place are we going to round to? Ones, tens, hundreds, thousands, 10,000s, 100,000s. Where are we going to? Huh? 10,000s, exactly. So we're going to round. These 2 numbers are going to be our only significant figures right here. Okay, so we're going to take a look at the number to the right of it, which is 5. Now somebody earlier today said 106,000. No, it's not 106,000. We got to round the 0 with the 5 right here. So it's 5 or greater, so we got to round up here. So this becomes 110,000. And you're like, wait, what about all this? It doesn't count. Okay, so I know we didn't do a division up here, but division, the same exact rules apply. Take a look at your final number, figure out which one has the least amount of sig figs, you round your final answer to that. Questions on this? Awesome. All right, adding and subtracting. A little bit different here. When we add and subtract, first of all, if you're adding and subtracting with sig figs, I really do suggest that you put them in a line like this. It's going to help you out. So match up each place. When I say that, I mean match up all the tens places, match up all the ones places, match up all the tenths, hundreds, thousands, whatever. Okay? Match those all up. It's going to be easiest for you because when you're adding and subtracting, your final answer down here has the same number of decimal places as the least precise measurement used in the calculation. Okay, so the first step that we need to do is figure out which one of these numbers was measured least precisely. And it's easy to figure that out, guys. It's the one with the least amount of decimal places. Okay? So, which number has the least amount of decimal places here? 18.0, exactly. 18.0. So we're rounding through to this place. The reason that we can't round to any other place is because we have no idea what these numbers are for this 18.0, right? This could be a 6 and a 4 if we measured it with something more precise. It could be a 5 and a 0. It could be 2 more zeros. We have no idea. So to preserve the integrity of this number, we have to round to the least precise place. Okay? So all we do then, we're rounding literally right here. Look at this number. Okay? It's less than 5. So our answer is just 31.1. Okay, last example for this. First step, remember, we always have to figure out which one of these is least precise. So you're looking up here, which one of these is the least precise? 1,500, exactly, 1,500. How do you know it? The last significant figure is right here, right? That's where we would have rounded to. Okay, so we have, once again, we have no idea what this could be, any of these. Okay, so we can't just assume what they are. So we literally have to round to this hundreds place here. Okay, because this could be 8, 0, 3, 4, whatever. We don't know. Okay, so we gotta round to that hundreds place. So now we know we're rounding to the hundreds. We look down here. We're gonna round to this 8. We look at the 4. It's less than 5, so we round down. So our answer is just 1800. When we do an estimation with big numbers like this, we don't really worry, if you look, we're not really using this 24.5 at all. It's just the way it is when we use big numbers. It's like when you get an estimation of how many people watch the Super Bowl. It's 56.5 million people watch it, right? Well, what about the 3 people that turned it off for after the national anthem? We don't say, oh, it's 56,400,990, you know what I'm saying? It's an estimation. Okay, we don't worry about those small values like that. All right. You can, actually I have something to pass out here. So I have a note sheet for you now. Okay, this is going to go into what you need for Intro 5. Okay, so on the sheet is some example problems I gave to you. So this is not something that you're going to be turning in. It's just something that you have so you don't have to be writing out full problems. Because there's some word problems on here. All right. Last thing we're going to do today. We got a couple examples to go through of T-charts. Okay. A T-chart is going to be something that we use when we're trying to do conversions. Okay, we're going to use them all the time when we get farther along in the semester. It's really, really, really important that we learn how to use this tool. Now, we're not trying to punish you by making you do more work by doing a T-chart, because some of the things that we're going to give you today, yes, you're going to be able to do them without the T-chart. We know that. The whole point of what we're doing with this is to learn how to use this tool so that when we get to more complicated problems, that's not an issue. Okay? So everything that we expect you to do in the homework today, we expect you to use a T-chart every single time. Even when we ask you how many dozen are there in 600 bagels. It's the first one. Like, I get that you can all just divide by 12. But I want to see you guys using a T-chart, how I'm going to show you how to use it right now. Okay? All right. So like I said, T-charts are for converting. Our first example that we're going to do is we're going to convert 10 meters into inches. Okay? Our step 1, and you guys can do this on the back of your sheet right now, you draw a big T on your sheet, just like this. Okay, step 2, will you put the number and the units that the problem is telling you to convert in the top left box. So in the top left box here, I put 10 meters. Okay, because that's what it's giving me to start out with. All right, next, you put that numbers unit. Okay, I cannot stress that enough. It says the numbers unit. You do not put the number down here. Okay, so don't put 10 meters down here. You just put meters. Okay, we're going to cancel out all units first. We'll put in all the values at the end, and I'll show you why. It's just so we don't get confused later on. Okay, so you put that, whatever's here, immediately goes down here. Like there's no thinking involved. You see something here, it goes on the bottom right when we do T-charts. Next, you're going to put the units that you want in the top right. Okay, so we put inches up here. Okay, for the sake of this, we don't know a conversion that exists between inches and meters. Okay, so what we are going to do is we're going to put something else in there that we can convert meters to and then convert to inches. Does that make sense? So we know that we can convert meters into centimeters. So now we get rid of inches. We'll put it down here. We're going to use it. We're going to come back to it later. But for now, because we can't convert meters to inches, we got to come up with something else. So we put centimeters there. Okay? It says on top step 4, we must convert meters to something that we can then convert to inches. And I'm telling you right now that there's 2.54 centimeters in 1 inch. So first we write centimeters in the top right. Now, we have centimeters up there already. Now, what happens is, we're going to draw another line, and we're going to start over at step 3. So now you have something on top that's not our final value, right? We're not at inches yet. So if it's up here, it's got to go down here every single time. So we take centimeters from here, we put centimeters down on the bottom right. Now I just told you we do have a conversion from centimeters to inches, correct? So now we can put inches on top. Okay, that's how we know when we're done with a problem. We can start adding our numbers in. Whenever the problem is asking us in this right box, then we know we're good. Okay? So, now we can start adding values in here. So I told you how many centimeters, what's the conversion for inches to centimeters? It's not always going to be 1 to something. This could be 12 to 42. Like it could be any numbers here. That's why we do numbers at the end. So, but what's the conversion between inches and centimeters, I told you? Right, 1 to 2.54. Perfect. Conversion between centimeters and meters?
100 to 1.
100 to 1. Right, so we write 100 here, and we write 1 by the meters on the bottom. Okay, we know we did everything right if all our units cancel out besides the final unit, because sometimes when we get farther in the year, we're going to have T-charts that are a lot longer than this. Okay, so it's going to be helpful to you to cancel your units out. Like if somehow I crossed centimeters out on the bottom and there was no centimeters anywhere on top, I know I did it wrong. Okay, so it has to cancel out. So I got centimeters here, centimeters on the bottom, meters here, meters on top. It's good. Okay, I'm left with only inches. Once I get to this point, things are canceled. I have all my values in. There's only one thing left to do, and it's solve this guy. And basically, you can think about these are all multiplication. So there's like a little x here, little x here. Okay, so you multiply by everything on top, and there's a reason everything on bottom is on the bottom of this line, right? You're going to divide by everything on the bottom. So multiply, 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 and then you divide, divide. So you take 10 times 100 times 1. I know we don't have to do times 1, but just for the sake of introduction here. Then you divide by 1 and divide by 2.54. So really you're just doing 10 times 100 and divided by 2.54. Okay? And that would give you 393 inches. Okay, so we know now that there are 393 inches in 10 meters. Okay, we're going to do the first one on the sheet that I just gave you. Yes, they're kind of weird word problems. It's like that on purpose because the hardest part when we get farther along in the year with T-charts and stuff is finding the information or the thing that we're starting with and seeing what the problem is asking us to find. Once we do that, everything else kind of works its way out. So, for this example, because we can convert anything like this, it says, Mr. Neubauer is having a packet party. Plans on having pepperoni pizza for his guests who love pepperonis. Each pizza costs $12, and there are 55 pepperonis on each pizza. How many pepperonis will there be in total if I have 6,590 cents to spend? Okay? So what I want to know is what am I starting with, what am I given, and what am I trying to get to at the end? So what is the problem asking me to find? What did you say, Dusty? amount of pepperonis. So I know at the end of this T-chart over here, I'm going to have pepperonis somewhere. Okay, the very last thing that I'm going to finish with is pepperonis. Okay, what is the problem giving me to start with? Now it gives me some conversions, right? It says that there's each pizza is $12. Okay, so that's not one value, right? It's telling me a conversion there. It says that on each pizza there's 55 pepperonis. So once again, that's a conversion, right? What's the one thing that it gives me that I can start with here?
Cents.
Cents, exactly. It says that I have 6,590 cents. So that's what I'm going to start with. So I'm going to put 6,590 cents right here. Okay, and then I'm going to start my chart out. Okay, you don't have to put pepperonis at the end because you don't know how big the chart's going to be, okay? I just wrote that on there for the sake of our example right now. Okay, so you would leave that till the end. It's just to show you that that's what we're trying to find. All right, so now, can I go from cents to pepperonis, first of all? Huh? No, I'm saying directly from cents to pepperonis. I'm telling you we can do it, but in one step. No. So what can we get cents into that's in the problem, or we can have another conversion here? Dollars, exactly. So first we got to take cents and put it down here. So we put cents down here. Okay, what do we say goes on top now? Dollars. So we'll put dollars up here. Okay, now if dollars are on top, where does dollars have to go? Bottom, right. It has to be able to cancel out. Okay, what can dollars go to?
Pizzas.
Pizzas, exactly. I'm not talking about values at all yet. We're just talking about units. It can go to pizzas, right? Okay, now if pizzas is up here, where does pizzas have to go? Bottom, exactly. We put pizza down here. Now, can we go from pizza to pepperonis? Yes. Perfect. So now we know we're good. We make sure everything cancels out. Okay, pizzas and pizzas, dollars and dollars, cents and cents. Beautiful. We have only pepperonis. Now we can plug all our numbers in. So how many pepperonis are there for a pizza? 55. Good. Okay, and then what about pizzas and dollars? What's our conversion here? 12 to 1. Perfect. Here we got dollars and cents. There's 100 cents and $1. Okay? So the last thing that we're going to do then is take 6,590, multiply it by 55, okay, and by 1, but whatever, we don't need to do that, okay? And then divide it by 100 and divide it by 12. That's not what I got. What did somebody else get? Huh? I got 302. 302 pepperonis. Okay, so there's a whole bunch of these on intro 5. There's a couple more on this note sheet. Please practice with those. Get used to these T-charts. Make sure you know what you're starting with, what you're ending with. Come with questions tomorrow for small groups, please. All right, you got about 2 minutes left. Just stay in the room until the mod ends.
Guys, remind me, intro 5, what you got. If you want, you can start doing some mini T-charts at the front.